Benvinguts, welcome all to this new session of the seminar. So you have Irene Macías, who's doing her PhD here to be, and she's going to talk about Moduli spaces of vector values.
So hello everybody, I will make the speech in English just in case. So today I'm going to talk about Moduli spaces of vector values. That is the motivation of the subject of my thesis, but in algebraic geometry terms. I will try to make the talk accessible for all of you.
Click on the PDF, please. Click on the
No.
Sí, sí.
Vale. Okay, so I'm going to talk about Moduli spaces. So in general, Moduli spaces are spaces that arise to solve classification problems. So the thing is to construct a space that parameterize the different classes of the objects that we want to study. So the model space, the points of the model space will be the different class of objects. So they were first constructed by Mumford, and he uses the geometric invariant theory. So the idea is that the two objects are in the same class if they are in the same orbit of a group action. So this will be the original construction, it's not the algebraic one. So for you to be familiar with Moduli spaces, an example is another concept will be, for example, the real projective space. There is a space that parameterizes lines that pass through the origins. Another example is the Grassmann. If we have a vector space and we want to parameterize the sublinear space of certain dimension, we construct a variety that will be the Grassmann. So these are Moduli spaces in another context. So in our case, the objects that we want to study are vector bundles. And vector bundles over projective varieties of dimension n. This kind of Moduli space was introduced by Murayama in 1970s, and the geometrical interest, I will not talk about schemes and shit, but just for you to know that we are also interested in this because vector bundles can be treated as locally feasibles. So just for you to know. So maybe you are familiar with other kinds of vector bundles. For example, this is an example of trivial bundle. So taking the S1, the circle, the cylinder will be a vector bundle of the cycle. We have a projection. And this is a trivial bundle because it's constructed by making the product of a vector space with a variety, a manifold, whatever. Another well-known example of vector bundle is the tangent bundle. We construct it by taking to each point, we associate the tangent vector space of our manifold or variety at that point. So there will be examples of vector bundle in another context. Now we move to algebraic geometry. So now we have to think of varieties in a different way. So for us, varieties are zeros of polynomials. So we take an algebraic coercive field of characteristic 0, and we consider the set of polynomials. So the affine varieties will be the zero of sets of polynomials. So for example, if we take the polynomial 0, we will get the whole space, there is the affine space because every point is 0 in this polynomial. And also for us, if we consider this polynomial and we see which are the zeros, we will get this curve. If we got the zeros, we get this curve. So for us, this will be also a variety. Also, if we consider this another polynomial and we draw the zeros, we get this curve, and this is also a variety for us. So the definition of variety changes a little bit.
I'm sorry, you're drawing me of this text. I mean.
Yeah, okay. Now yeah, because we are fine ones. Yeah. But now, as I told you, we study projective varieties. So now we, instead of in the affine space, but in the projective space, the points will be denoted by those coordinates here. And we study homogeneous polynomials. So we work with homogeneous polynomials that are sums of terms of the same degree. And they form another rings that which fixes the set of polynomials of the same degree. So by studying the zero of homogeneous polynomials, we get projective varieties. So the idea is the same in the other case, but now in the projective space. So for example, we have S as a set of polynomials. A variety would be the points in the projective space, such that all the polynomials in our set is 0 in that point. So for example, again, if the polynomial is the 0, we have the whole space. Now it's the projective space. And another example will be this one, that maybe is more difficult to see. But if we have these two polynomials, and we want to see the zero block of these polynomials, we get the union of two projective points. So this will be another example of projective sets. So we want to study vector bundles that they did the same as before, but now our variety changes. We are now working with vector bundles over projective varieties. So the idea is the same. So a vector bundle will be an example of a kind of a linear fibration. So a linear fibration is something that projects into in our variety, such that for each point of our variety, if we take the inverse image, we get a vector space over the field. And we will denote it in this way. If we consider an open set of our variety, we will denote it this way, the restriction of our linear fibration to this open set. That will be the inverse image of all these open set projected to the open sets. So a vector bundle is a kind of linear fibration that works good locally, is the idea. So we have a linear fibration that is locally. So for every point, we have an open neighborhood such that this restriction is isomorphic to this. So locally, it looks good because it looks like this set. So what this means is that gluing preserves the linear structure. So if we think our variety as with a covering of open sets, we can define the vector bundle good locally, and we can pass from one open set to another in a good way. That will be with regular functions. So in another context will be this. If you have here an open neighborhood of a point in the circle, this will be the restriction of the vector bundle to this open set. But if you see, this will be the open set product the real line. So locally is good. Okay, so I will put two examples of how we will define vector bundles with the right geometry, just for you to see how it will be. So one example of vector bundle is the cotangent bundle. That is the dual of the vector bundle. And so now, for example, for the case of the projective space, we consider this covering. We consider the points where one coordinate is non-zero. So in its open set, the differential form will be this expression. So the cotangent bundle is the dual of the Mendelian bundle. So for each point, we find the differential form that is in this way locally. And this has a local structure, so it will be an example of vector bundle. This will be another example of vector bundle, but you may only understand this if you are more used to work with algebraic geometry. But okay, we are in the projective space, and we take the covering as before. So this is the ring of polynomials and quotient by an ideal of a polynomial. This approach is the analogous of taking the prime ideas, but in the projective space. So when we construct this, there will be like the prime ideas of this coordinate wheel. Okay, so this will be an example of vector bundle. Why? Because if we restrict this to an open set of this form, we get a regular function. We get a function that works good locally. And we can go from one open set to another by multiplying by this. There will be also another good function. So this will be an example of rank 1 vector bundle over the projective space. Another definition that is used in vector bundles is section. So a section is a map from the variety that we are making over the vector bundle to the vector bundle, such that if we compose it with the projection, we get the identity. So for example in another context would be this thin, the red thin will be a section of this vector bundle, because if we make this and we compose, we go back to the start. Okay, so another thing that we have to define is isomorphism between vector bundles, because what we really want to classify is vector bundles that are isomorphic. So if we have two vector bundles, isomorphism is a map that was grouped with the projection. So if we compose it with one projection, we get the another one, and restricted to the fiber is linear. So This will be the piece of vector bundles, and we can talk about isomorphic vector bundles and also subvector bundles of another one. One vector bundle included in the bundles. So coming back to the problem that we wanted to solve is to parameterize isomorphic classes of vector bundles over predictive varieties. But we will classify vector bundles with state and fixed invariants. One invariant of the vector bundle is the one that we have already seen. And another invariant of the vector bundle is the chair class. The chair class, the idea is, given a vector bundle, we get elements in this ring that is called the chunk. So maybe you're more familiar, I don't know, to characteristic classes of vector bundles, that given a vector bundle, we get an element in the homology of the surface, well, of the variety. So this idea is the same, but now instead of homology, we work with this ring. But the idea behind is the same. So we want to measure how trivial or non-trivial is our vector bundle by considering elements in this ring. And the idea is that we make this correspondence by starting this section, but I don't want to enter in that. So we just, given a vector bundle, we have elements in the theory. So I will introduce what is the theory. So the theory is a ring generated by the closed irreducible subvarieties of our variety. So we have cycles. The cycles are elements of the abelian group generated by these closed reducible subvarieties of our varieties. And between these cycles, we can define an equivalence relation. And so we will have cycles of with the same codimension, and we define this equivalent relation. We get these classes that we denote in this one. So between these classes, we can define a kind of product. And then we form a gradient ring. There is this ring. That is what we call the Chow ring. So in this ring is where we take elements from vector bundles. So as I said, a vector bundle gives us an element here, and there are invariants of the isomorphic class of the vector bundles. So now coming back to what we want to create an algebraic variety. Well, it will be a scheme, but something that has a good algebraic structure that parameterizes our isomorphic class of vector bundles with these fixed invariants. The problem is that if we consider all the vector bundles, the set that we get has not good algebraic structure. It's not an algebraic variety, so we need something else. To fix it, what we do is to define a condition that vector bundles should have. And this condition is called the stability condition. So if you consider the stable vector bundles, this set will be an algebraic variety. So we need to define this condition, and I will define it for the case of surface. So right now we were working with varieties. Now we work with dimension 2 varieties. But the definition will be analogous. And so this condition, the stability condition that we want our vector bundles to have, depends on a divisor. A certain kind of divisor that is the ample divisor. So first of all, I have to introduce what are divisors. So the idea of the divisors using algebraic geometry is a generalization of subvarieties of codimension 1. For example, subvarieties of codimension 1 in a space will be groups. Okay, so a divisor will be a linear combination of these subvarieties of codimension 1. We define a product between two divisors, and we also have a equivalence relation. So call it linear equivalence. So the divisor under this equivalent relation form a group that is the typical group of our variety, or in this case, our surface. If you notice, we are working with codimension 1 variety. So coming back to the elements in the Chow ring, if we consider the first in class, we are talking about also the codimension 1. So we can see the first in class of the vector bundle as an element in the typical group. So roughly speaking. So we have this definition of divisors that they form this group, and we are interested in one kind of divisor, the ample divisor. So roughly speaking, ample divisor defined as an embedding of our variety in the projective space. or this will not be exactly this, but this is the idea. So we fix one divisor of this kind, and we can define this stability condition that is respect to this sample device. This stability condition depends on this function. So we have a vector bundle with fixed invariants. So it has rank R and it has 10 classes. We take the 10 class that we can see it as a divisor, and we fix an ample divisor. So we can define this function. This will be the intercepted product between the first 10 class and our ample divisor, and then this will be the rank. So this is no more than a rational number. So we can, one thing we fix an ample divisor, we can define this function. Okay, so the stability condition, the definition of a vector bundle to be stable, is given by this function. So we have this vector bundle of vector rank and 10 classes, and we fix an ample divisor. So we say that this vector bundle is stable with respect to this divisor if all the vector bundles are in E, so also vector bundles P with different rank and non-zero has the value of its function less than the value of the function of P. So this is the condition that we want our vector bundles to have. So it's important to see that it depends on an ample divisor. So we first fix the ample divisor and then we define the stability. So for example, the cotangent bundle, as I said before, is an example of an unstable vector bundle. Okay, so now if we consider all the vector bundles the stable ones, we do get an algebraic variety. So if we impose the vector bundles to have this condition, we get what we want. We get something that has good algebraic structure that parametrizes our isomorphic class of vector bundles. This is what I denote in this way, this is what we call the Moduli space. Here, as we are working in surface, we will only have 2 term classes because we don't have termination things. But this will be the notation for Moduli space of values. Okay, so I told you that this is the subject of my thesis. So what is interesting about Moduli spaces? Okay, the geometry of Moduli spaces can give us information about the geometry of X. That's why it's important to study it. And there are several questions about its geometry that we can ask. For example, as I said before, the definition of stability depends on an ample divisor. So we fix an ample divisor and we say, okay, the vector bundle should be stable with respect to this ample divisor. But what if we could take another one? The Moduli space that we get is the same, is different because the definition depends on the divisor. So they may change or they not. Well, the question is that it depends. There's some relation with the ample divisor. The Moduli space stays the same or is birational, and in other cases, it's totally different. So for the case when the rank of the vector bundles are 2, this is was studied first by the team, and this is what we call the Walsh and Chambers theory. So this theory studies whether or not the Moduli space is changed when we change the polarization. That means the ample divisor. We can also see the smoothness of the Moduli space, or the dimension of this Moduli space, and also another things like reducibility or rationality. And these things will give us information about the variety X. So for the case of surfaces, this is a general resource, or you can find it in a book of Daniel Hurwitz and Martin Lane, that is about how is the Moduli space for the case of surfaces. So we have a projective surface and an ample divisor of the surface, and we consider a vector bundle with these 10 classes. In this case of surfaces, the second 10 class it will be the integer, so it will be an integer number. So the results say that if we take the second 10 class very big, we know how the Moduli space looks like. It will be smooth, irreducible, or projective variety, and this will have this dimension. So for the case of surfaces, if we take these big values of the second 10 class, we know how the Moduli space is. So we will work with this kind of Moduli spaces because we know how they look.
What's this G?
This is the genus. This comes from the characteristic, color characteristic of the vector bundle. Yeah. the Euler characteristic of the vector bundles that come from the homology group. This is another geometric unit. Okay. So now I will introduce what is the Brill-Noether theory. So this is the subject of my thesis. So one way of studying the geometry of the model space is look at subvarieties of the model space. So we define some kind of subvariety of the model space. So these varieties depend on the cohomology of the vector bundles. So if the cohomology of vector bundle is less than or equal than type, we say that the vector bundles are in these subvarieties. So the subvarieties has the Brill-Noether locus are the one that each points are a stable vector bundle with this dimension more than or equal than. Okay. The interesting thing we notice in this way. The interesting thing is that it gives us a filtration of the model space. So we will have an stratification of the model space. So by studying the subvarieties, we can have information about the model space. So the first Brill-Noether theory, the classical Brill-Noether theory, was in the case of rank 1 vector bundles, line bundles on curves, on algebraic curves of delta genus. So here the model space is the typical group of the curve. And so we get the line bundle, we study line bundle with at least k+1 independent realization. So this will be the classical idea. So this is the origin, but we can generalize it in two ways. On the one hand, we can study higher rank vector bundles on curves. On the other hand, instead of curves, we can take a surface or an algebraic variety. So we can generalize it in two ways. So this generalization was made by Rosa Maria Miro and Laura Costa. So they define these subvarieties for any algebraic variety of dimension. So it was defined for curves, and now we define it for any algebraic variety. So the interesting thing is that the Brill-Noether locus can be is a calibratory variety. There is a variety defined by the set of minor submatrix, but it's a good algebraic. It has a good algebraic structure. So they say that it will have a this for surface, but it was stated. So it will have a surface or a variety, and we consider a vector bundle stable with respect to a polarization that we fix H, and we ask the vector bundle that the cohomology group is 0 for E more than or equal than 2, then there will exist these Brill-Noether groups. There will be an indeterminate variety which supports which points are these stable vector bundle with time dependencies. So we can define this theory that was proposed for any algebraic variety. So this is what I studied. And as it has a determinate variety structure, we can talk about the this dimension. That this dimension is the expected dimension. That means that we know that this Brill-Noether locus that we define has dimension more than or equal than this, for sure. There are sometimes that it has the exact dimension, sometimes not, but we know that dimension is at least this. And also they prove that we have this inclusion, and this inclusion is what gives us this filtration that I said before. So if we have this condition, we know that this Brill-Noether locus exists, and so we can study the model space by studying this stratification. And we can also we also know how the dimension of these subvarieties is. So to finish this, I want to say what you can study about this. So first of all, you can study whether these subvarieties are empty or not. We can also study how is the value of this expected dimension, because we know that the dimension of these subvarieties is more unequal than this one. But if this number is less than 0, this will mean that the subvariety is empty or not. This can be a question. We can also study the smoothness of this Brill-Noether locus that will give us information about the smoothness of the model space, and the same about irreducibility, or we will find irreducible components of the expected dimension. So just to say that by now, I have got whether or not these subvarieties are empty with one kind of surface, the real surface. And also, we know that this question is not true because we find some subvariety that has this expected dimension negative, and it was not empty, so it's not true that the sign of the expected dimension made the subvariety empty or not. And also, we are looking at some results about this. So this was everything I wanted to say about. I hope you enjoyed it, and thank you.